Alright. Let's do a little review.
Mrs. Cool.
Yeah, this is from someone else. So, how do nuclear power plants work? Do y'all know how nuclear reactors work?
Yeah, they got nuclear. I knew one blew up because people.
How do we produce almost all of the power in the entire world? How do we produce almost all the electricity?
Oil, gas, generators.
How do they work?
Gas react with air and electricity.
There you go, agua.
H2O. We got that water power, son.
So what do you mean by? So dams?
Yes.
No.
Like.
I got anything.
Yeah.
Jesus, those damn on a fishing.
Cool down. Are almost water turbines? Yeah.
They're like wind turbines.
How does a coal power plant work?
If you just burn coal and it makes, I don't know. To be honest.
Y'all are like super close. I'm not.
You're just like throwing that coal in.
Okay, yeah. It uses water.
I know how it works. Shut
Ah.
up. It's like steam engine. So it basically the water flows through the whatever.
Mhm.
I don't know how. Or it's like a turbine or something pushes the water.
Oh, you've been in the creek and you know how.
Y'all let her talk. He's right.
It cools down whatever's inside there. Then the water flows out. As warm water and just recirculates through the whole thing again.
So basically, right. So what we have is a tank of water. We have a tank of water. What does water turn into whenever it's heated? And what happens if you increase the temperature of a gas? It builds up, and keep y'all's mask on, and Tamara, lift your head up.
Can Tyler Bennett run by the office just
Yes,
for
again.
a minute, please, sir?
So what happens if you take a Coke can and throw it in the oven?
It's gonna pop.
Why?
Because because the air expands.
The pressure. So as we heat up water, it turns into steam. And if I have, for example, some sort of turbine, which is just basically a fan, then as this pressure builds up, it's going to force the steam to turn this in a circle. And this is basically a generator. And we do some magnets and some electrical wires. If a turbine or motor spins, it produces electricity. If you just take any motor and hand spin it, it produces electricity, or you can do it in reverse. You can run electricity through a motor and it'll cause it to spin. It works both ways. You can either run electricity through a motor and it causes it to spin, or you can spin the motor and get electricity.
One of those flashlights?
Yes. So as the steam pushes by, we eventually have a condenser where it collects back into water and we cool it off. And then we have a pump system that pumps it back into here as it's cold water. So we have cold, we heat this up over here. This is basically how most of the electricity, and y'all keep y'all's mask up, how most of the electricity in the world works. So what does a coal plant do? A coal plant burns coal to heat up water. And then the water turns into steam, turns to turbine, gets cooled off, pumped back in, and that system repeats. Natural gas plant. Natural gas burns as natural gas, what heats up water. Some solar plants uses mirrors, and they have basically some mirrors with a long tube of water. So we have a mirror here, and we have a long tube of water. The mirror bounces light off into the water, which heats it up, turns into steam. Steam goes down the tube. It turns a turbine, electricity. What does nuclear plants do?
Nuclear plants just does all that, but with nuclear stuff.
They heat up water by nuclear decay. Almost all of our electricity production is basically just heating up water and turning it into steam. We do have dams. How dams work is if we have water what's really high up, we can cause by gravity, have the water falling down by gravity, and we just put a turbine in right here. It causes the turbine to spin around as water falls off the dam. We have actual solar power using solar cells, where light is absorbed, photoelectric effect. Then we have wind turbines that has wind blowing through the turbines, causing it to spin. But the majority of the power or electricity we produce is basically ends up being heating up water, turning into steam, turning a turbine. So how much energy is held in a small bit of matter? You can just think of a nuclear bomb.
Was Fat Man dropped on anybody specific?
No, it was dropped on Nagasaki, I believe. There's a lot of energy in matter. If you have a basement, you should be concerned about radon. Radon is a gas that's radioactive. It's constantly seeping through the ground. Usually it's harmless. It is extremely radioactive. But usually once it reaches the surface, it'll float up and it won't collect anywhere. It won't stay attached to the surface. But if you have a basement, it can build up in your basement. And your basement can be radioactive. So remember this notation, a little review. The top left number is the mass number. It's the number of protons plus number of neutrons. The bottom left number is the atomic number, which is the number of protons. We have a special word for protons and neutrons. They're called nucleons, meaning something that's in the nucleus. And again, remember, protons want to get as far away from each other as possible. They're both very strong positive charges, and positive charges repel.
Bambi, come on from office, please. It's Bambi.
And how we get them to stay together is through the strong force. Nucleons, meaning protons and neutrons, are held together by the strong force. This strong force contains a lot of energy holding these nucleons together. If you were to separate a neutron or a proton from the nucleus, it will release a lot of energy. Remember also, atoms of a given element have the same number of protons, the same atomic number. That determines what element it is. But different numbers of neutrons. So, for example, the most studied element in the universe is the hydrogen, and it's 3 isotopes. We mostly look at just the normal 1 protium, which only has 1 proton. But we can have deuterium and tritium. The 3 in tritium corresponds to how many nucleons it has, or the mass number. So 1 proton plus 2 neutrons. And to figure out how many neutrons it'd be 3 minus 1. So, different isotopes can be stable or unstable. Carbon-12 is extremely stable, meaning it doesn't break apart. Carbon-13 is mostly stable, but carbon-14 and the rest of them are very unstable.
How come carbon-11 and 13 is stable, but 14 and 15 is
It's not, carbon-11 isn't stable, they just didn't label it. Only carbon-12 is truly stable, varying. Let me look it up. So isotopes of carbon. I can tell you exactly how stable they are.
what, 9?
looks complicated.
So carbon-12 is stable. Carbon-13 is stable. I didn't realize carbon-13 was also stable. So these never decay. They will stay carbon-12 for billions and billions of years, or carbon-13. Carbon-11 has a half-life of 20 minutes. So if you had a pound of it, after 20 minutes, a half a pound would decay away. Carbon-10 is like 20 seconds. And then the farther away from carbon-12 you get, it's almost instantly. Carbon-14 is what we use radiocarbon dating. Is a half-life of a little less than 6,000 years. 5.7 millennia.
No, it's still stable.
It's not stable. Stable means it doesn't decay naturally. This means that after 5,730 years, half of it will decay. So if you had 10 pounds of carbon-14, after 5,730 years, half of it decay away. So 5 pounds will decay, leaving you with only 5 pounds left. And then the rest of them are extremely unstable. For the most part, only carbon-12, carbon-13, and carbon-14 are found in nature. The rest of them are not usually found in nature. So, radioactive isotopes are isotopes of certain unstable elements that spontaneously emit particles and energy from the nucleus. They just randomly decay. John, lift your head up. Camera.
Please, John. Come on, why Hiroshima here?
I am too. I've only had like 2 hours of sleep last night. Fortnite.
Nice. For real?
Yes. So,
Gotta get to
in 1896, Henry accidentally observed radioactivity of uranium salts that were fogging photographic film. His associates were Mary and Marie Curie. Any of y'all heard of Curie?
Platypus?
Mary Curie?
Oh, no. No,
She was very well known in her influence of radioactivity. Did y'all know that, so how film works back then is it has to be exposed. And it, basically if light falls on it, it'll start, rendering or whatever with special light. During the 1940s and 1930s, do you know, I think it was AT&T or Polaroid or some company, they could actually tell every time the United States was doing nuclear bomb testing. And they basically went to the United States, what's going on? My film is constantly being screwed up by some unknown radiation. And they actually pinpointed where they were testing at. And it was like a closely guarded, top secret thing. The United States government made a deal with them that they would give them, they'd give them like 10-hour notice before a nuclear bomb, so they can turn off all and shield all their film. But it was like a most guarded secret in all of America was nuclear bomb testing, and some companies actually figured it out just because of the effects. What Henry did was he had some film that he was going to develop later, and he had to keep it in a dark light and expose it to certain lights. And he accidentally had a uranium rock, and he accidentally put it on top of it. In a completely dark, he put it like in his desk, completely dark, shielded from all light. And then he came back and he looked at this film, and some light source, it was the radiation, caused it to be exposed. And he knew that since it was locked away in his cabinet or desk, the only possible source was from this rock, uranium. Mary Curie, born in 1867 in Poland. Her original name was Maria, or I don't know how to pronounce it, it'd be Slavic. She discovered lots of radioactive elements. She actually carried around a sample of very highly radioactive chemical in her pocket. They had no clue the dangers of radiation back then. She, yeah, she died in like her 30s or 40s. They didn't know what radiation was. Remember, during this time, they had just figured out what an atom was.
That's where the radiation is.
They had discovered an atom in 1807, and they had no clue what an electron was. The electron was somewhere around this period. But she was a winner of the Nobel Prize along with physicist Henry, I don't know how to pronounce his name, Becquerel,
Then she died.
and her husband, Marie Curie. She was the sole winner of the Nobel Prize for chemistry. So there are going to be three main types of radioactive decay we're going to be working with.
How did she get problems we did?
She wasn't dead yet.
And did that
She also had a
radioactive piece of fucking
longest
factory
press.
Yeah, she got cancer. But they didn't know that about cancer either, really.
Huh. She's not that radiation.
This chick, she's a bad doctor.
Guys, if y'all were to go to the water fountain right now and it had been laced with arsenic, how would you know? It's tasteless.
But then we need to text because I would know.
The water here is so bad.
Again, they had no clue. Actually, here's an interesting thing. Do y'all know y'all's glow-in-the-dark watches?
Yeah.
Do y'all know what it used to be done?
Used to be or is the?
It used to be a radioactive, not radon, radium. It used to be or tritium, maybe. I think it was tritium, hydrogen mixed in with it. It was radioactive paint. And back in this time, women worked at these factories. Cody, quit. But what they would do is they get a paintbrush that basically has hair at the end of it, and they would dip it in the paint, or they put it in their lips to straighten it out, dip in the paint so it's very straight, and then paint it onto watches. And to get the end of the paintbrush very fine, they would basically do with the lips. And again, they had no clue about the dangers of radiation back then. They didn't even know what radiation was. She was the person who actually discovered it, but she just discovered what radiation is, not that it was dangerous or anything.
Before she died from it.
So, three major particles.
Man, he always liked me back then.
The alpha particle. It is 4-2He.
I have a question. Was there kind of radiation on top of the shit? That's confusing for me.
It wasn't that radioactive. Otherwise, she would have died like very, very quickly. But like a lot of her stuff, her bones and everything had to be sealed off in like a lead casket.
What are the odds of mutation?
High if you're exposed to it for a long period of time. So this is a helium's nucleus. Not like that.
Stuff on wings.
We have a beta particle. Note, it is slanted slightly. It has this long tail. This is the Greek letter beta.
So, Greeks believed in a letter and a word.
What?
Yeah.
We have the same thing.
So,
Latin alphabet's the same thing. I, A, B, C. We call it B. I could spell it B like this.
O-B-E.
And then we have A. The thing is, we Latinized the spelling of their words. They would have just said this is alpha. We actually took the pronunciation of alpha and made a Latin word out of it. They could have easily took our letter A or our letter B and did something like this. Beta, epsilon, epsilon.
What's epsilon?
The Greek letter E.
Oh, epsilon.
It's this. This is just a highly energetic electron. We have gamma.
Human radiation problem.
You'll note something different. So we consider the electron not to have any mass, so its mass number is 0. When doing nuclear notation, we let the bottom left number basically represent charge. So it has -1 for the electron. We just give electron a -1. Gamma is an electromagnetic wave. Very highly energetic. Then we have the beta plus particle, also called beta plus, or so beta plus. Based off this symbol right here, what do you think beta plus is?
Positive.
Positive electron. Called a positron. It's antimatter version of electron. Then we have a neutron. It's just the letter N. Neutron has a mass of 1, no charge. So the neutral neutron. And let's see, we won't worry with them too much, but neutrino. And there's different varieties. We won't worry about neutrino, but I'll just write it here. Neutrino is a special particle. That's that has multiple different types. I'm trying to see which one. There are electron neutrinos. Symbol is we have muon neutrinos. And then we have tau neutrinos. We won't be looking at neutrinos, but they are different material particles that can be made. And then there's antimatter's version of them. They're mostly there to balance out equations.
Celeste,
Yes.
have you ever watched Chernobyl?
So alpha decay is the emission. Guys, quit talking about unrelevant stuff. Emission of alpha particles. So it's just a helium nuclei, 2 protons and 2 neutrons. It has a charge of +2. Can travel only a few inches through the air. So this means that it can be stopped by a sheet of paper or clothing. In air, alpha particles don't really go too far. However, if you ingest something, guys, wake up. Lift your head up. If you ingest something inside your body and is emitting alpha particles, it can wreak havoc on your body. Even though it's normally stopped by a sheet of piece of paper. It will stop by your outer layer of skin, usually. Your outer layer of skin is dead, so it doesn't matter if you destroy your outer layer of skin. You have a few layers of dead cells covering your whole body.
That's what basically did it. No, I mean, exactly. Yeah, so it would be safe from the public. Yo.
So let's look at an example.
Can I get back before we do the example?
I'm doing it. So let's say that uranium 238 undergoes alpha decay.
When it's just good then.
So what is going to happen? We're going to have 238, 92 uranium. And it's going to split apart into something and a alpha particle. This is your alpha particle. So we have we have 146 neutrons. That's 238 minus 92. And we have 92 protons. And what's happening is it's breaking apart into something else. This is uranium. And I'm not going to write that. This is uranium. And it's releasing an alpha particle. 2 protons and 2 neutrons. What is this chemical? What is this element that is made over?
Don't know.
You can treat this arrow almost like an equal sign. So 238, let's look at these top numbers. So 238 is equal to something plus 4. What plus 4 gives you 238? 234. And then we look at the bottom number, 92. The arrow can be treated as equal sign. It's equal to something plus 2. 90. What has an atomic number of 90? Again, this whole unit, y'all need y'all's periodic table.
Beryllium.
No, thorium. And thorium has 90 protons and 144 neutrons. So the neutron count went down by 2. The proton count went down by 2. So the mass number drops down by 4. This is basically, this right here, this math right here is basically going to be the entire unit.
Nice. Simple. Complicated.
So this is alpha decay. Is whenever the nucleus emits an alpha particle. It just spontaneously loses an alpha particle. And when it does this, it changes what the element is. So we have a large unstable nucleus that emits an alpha particle, becoming a smaller, more stable nucleus.
Alpha decay can work with everything, right?
Yes. Well, not everything. Obviously, a hydrogen atom can't go under alpha decay. So let's look at beta decay. So, again, we're not worrying about electrons.
Me trying now.
What is a beta particle? A beta particle is a highly energetic but we don't concern ourselves with electrons. Where do you think this electron comes from? We're only concerning ourselves with the nucleus. It actually comes from the nucleus. Beta decay is when a neutron, decays into a proton and an electron plus a neutrino. But we don't need to concern ourselves with a neutrino. You can ignore the fact that neutrinos also emitted. So let's take our previous example. So we have 238 uranium. It undergoes alpha decay and becomes thorium-234 and an alpha particle. Now, thorium-234 undergoes beta decay. So that means something plus a beta particle. So what is this something that's left over? Same thing. We'll go look at the top numbers. 234. Let me up inside. 234. We can use the arrow as an equal sign, equal to something. This top left number. So top left number equals top left number plus 0. What plus 0 is 234? 234. So now let's do the same thing with the bottom numbers. 90 is equal to something plus -1. So 89 plus -1 is equal to 88. 91. Again, if you're adding a negative number, it's the same thing as addition. Subtraction. So what -1 is giving you 90? And 91 is polonium, or it's this word, protactinum. So it actually the nucleus actually went up in atomic number. It still lost mass, or the mass stayed the same. So it started with a mass of 234 and went to 234. So the mass stayed the same, but the atomic number increased. Gamma decay. Gamma radiation, it's electromagnetic energy that is released. Gamma rays are electromagnetic waves. They have no mass. Gamma radiation has no charge. It means it's the most penetrating and can be stopped by 1 meter thick concrete or several centimeters of lead. Forgot. Go back on beta. So beta decay is electrons ejected from the nucleus when neutrons decay. Beta particles have the same charge and mass as normal electrons. They're just moving crazy fast. Michael, lift your head up. Thomas, lift your head up. So they can be stopped by aluminum foil or a block of wood, and no. So if you have a block of wood, basically these walls would stop beta decay. Or a thin piece of aluminum foil would be able to stop it.
What name did you foil?
So basically a neutron becomes a proton and emits an electron. And this is the example I just did. In gamma decay, what is going on? In gamma decay, we have these energy levels around the nucleus. And so normally the second energy level would have 8, but an electron's in a higher energy level. Whenever an electron falls down to a lower energy level, it emits an EM wave. It emits, in this case, for radiation, it emits a gamma radiation. So what's happening is that electron is eventually going to be captured by an atom and fall down into a lower orbital. And that's gamma radiation.
That's complicated.
It doesn't do really anything in calculation. So, for example,
Do we have homework?
it's not today.
I want to go to the So I know if you had it.
So let's say that nickel 61 undergoes gamma radiation or gamma decay. So we're going to start out with nickel. And the atomic number is 28. It's going to make something plus gamma. Gamma has a mass of 0, a charge of 0. So what plus 0 gives you 61?
61.
What plus 0 gives you 28? What element is 28? Nickel. And that's it. The challenging thing here is if I ask you the other way. 61, 28 nickel turns into 61, 28 nickel plus something else. So 61 plus what gives you 61? 28 plus what gives you 28? And what symbol has 0 and 0?
0.
Gamma. So you have to remember that 0, 0 is gamma. That's the tricky part. You have to remember gamma is 0, 0.
That's hard to remember.
I don't know. I just shuffled it fast.
So
Okay, bro. I'll walk by and take a picture of your chest.
So polonium undergoes some sort of type of radiation and turns into lead. Plus some unknown chemical or thing. So what would go in here? 210 plus something gives you 214. And 84 the bottom numbers is equal to 82 plus something.
The 4 and 2.
So 4, 2, and 4 and 2 corresponds to helium. So what this is alpha decay.
So helium is being alpha decay. So helium is alpha decaying.
The helium nucleus is alpha decay, yes.
Not always decaying.
And it's decaying the PO to make the PB.
So usually, I'll say this too, hydrogen is usually written like this, but we can also write it as a proton. So this would be a proton.
And neutron.
And this is hydrogen. They're the same thing when we're concerning ourselves with a nucleus. Hydrogen 1 and a proton are the same thing. So a proton turns into a neutron and emits something.
Electron.
What does it emit? So again, we look at the top numbers. 1 arrow is an equal sign. 1 plus something. And the bottom numbers, 1 equals 0 plus something. So what's the top one?
0.
0. So it goes up here. What's here? 1. So what has 0 mass and 1 at the bottom?
Hydrogen.
Hydrogen has a mass.
No.
It's written right here. 1, 1.
Oh,
Beta
I thought
plus.
it was 2 lines you put there.
So it's a positron emission.
What's a positron?
Antimatter. Positively charged electron.
Okay. What's a negative charge?
I call it an electron.
Call it negative charge. Okay.
So this is beta plus decay.
I should have listened to the negative charge. Yeah. I thought it was so wrong. That sounds wrong. You just said that. Wait, I didn't know. Beta, alpha, and gamma.
So gamma just had a sided nucleus, which is another possibility. One of the nucleus can be a sided. Doesn't have to be an electron. So alpha particles can be blocked by a piece of paper. Beta particles can go through paper and your clothing, but be stopped by aluminum. Gamma can go through all of them, and it takes several centimeters or inches of lead to be stopped.
So, if anything, if we want to make a bomb shelter, we need to make it out of lead.
Mm-hmm.
Okay. Why not? How expensive would that be?
Very.
Okay, I will get one. I'll get my buddy to
So we have, which one has the highest frequency?
Gamma.
Gamma. It goes up and down very fast. So which one is more penetrating? Light waves, X waves, or gamma rays? Gamma. Then X-ray, then light ray.
Yeah.
So I wish this wasn't so expensive, but do y'all want to see radioactivity in real time?
Yes.
More money than you.
Uh,
You can't put a price on someone's life. Me too.
The black market guys.
Your wallet. However much you got in your wallet, how much your life is worth.
so this is called a cloud chamber. It takes super cooled vapors that want to turn into solid crystals, and whenever a charged particle goes through it, it causes it to condense into a cloud.
So those are the two that
Every line you're seeing, and this is in real time, is a charged particle moving through the cloud.
those are the two that Deadpool put in. It looks so cool. John, was Deadpool put in a contraption with the oxygen got sucked out of it? Yeah. I thought he did.
The oxygen got stuck out of it, Tom went to why would he go like that, man?
They put stuff in it, like radioactive stuff. That's what turning into.
But technically, If you went to, you could swim and not die from it. When you swim, like go underwater and just swim forever to not die from it.
I'm showing how big he's
He would pass out. But he wouldn't die. He would die.
He would pass out, wake up, swim a little bit more, pass out, wake up.
Yeah, he would just pass out, wake up, pass out. Like he would wake up with no capacity on, so he just pass out again. So it's being an endless cycle.
If you really wanted to keep that course to stop, just like still, you just put it in the water.
He's on the way to the good boy. Stop today. Put him in water. Michael, what? He found a way to kill Deadpool. You can't kill Deadpool. You can't kill